Okay, we're going to get started with the next talk.
Okay.
Great. So, our second speaker of the morning is Kiran Kedlaya, who will give us his last talk.
All right. I think I'm live. I'm about to pick up where I left off last time, but before I do that, let me take a few moments to, in some sense, give a little bit late the introduction that tells you where I'm trying to go with all this, which is, well, in the process, let me also summarize where we've arrived at. So far, so we've talked about this kind of construction that turns, say, perfectoid spaces into some sort of relative curves. So we've defined relative Fontaine curves over perfectoid spaces. Well, mostly we talked about doing this over this SPA of a perfectoid pair, but the construction certainly glues. I'll continue to talk about it over an affinoid perfectoid base, but we do have a definition that makes sense that sheafifies, if you want. It glues. So we have this this object, Farg Fontaine, over a perfectoid base, which has some kind of a projection map at the level of topological spaces, like so. I can just point out as a preview that we'll see a little bit later how to actually write down a legitimate map on the level of the diamonds that Jared introduced last hour, but never mind that just yet. We have at least something that in some fake sense behaves like a bundle of curves over a base. And we know that this thing has interesting properties. We know that if you have a point, which is to say SPA of a perfectoid field of characteristic P, the vector bundles on this thing, so to speak, capture p-adic representations of the Galois group of F. So this was via the theorem that I ended with last time, and now I guess to the Narasimhan-Seshadri theorem, that said that there was an equivalence of categories between certain vector bundles, stable of degree 0, and the category of p-adic representations. So we've done something that kind of traps the objects of interest in p-adic Hodge theory, p-adic Galois representations, inside some kind of geometric framework. In a moment, I'll say precisely how this extends to a statement over a more general base, but so keep in mind that there will be some version of this that makes sense for representations of fundamental groups of more general spaces. So that sort of suggests that in order to understand families of p-adic representations, or it's a sort of moduli of p-adic representations if you want, this suggests that we should study moduli spaces of vector bundles on these relative curves. So what is a moduli space? It's some sort of object carrying a universal family. So it would be some sort of object down here such that the relative Fontaine curve over that had some sort of universal bundle. That every bundle I could ever write down would somehow come from that as a pullback. Now, as usual in algebraic geometry, moduli spaces are kind of tricky things to actually get your hands on. Often you don't find them in the categories where you start working. So, for example, you won't find one of these things in general in the category of perfectoid spaces. You have to so you have to enlarge to certain categories of stacks, hence the word stacks in my title. So stacks are in some sense a way to dodge the question of building a geometric object by simply thinking about the functor of points that it would correspond to, which is to say, in this case, it would be the functor that turns, say, a perfectoid space into the set of isomorphism classes of vector bundles on this relative Farc-Fontaine curve with certain extra properties, say some semi-stable property, some degree property. Perhaps if you don't want to just think about vector bundles, you might want to think about, so vector bundles are, so to speak, torsors for the general linear group of some rank. You might think about more general algebraic groups. Come to that in a moment. So for most of this talk, I'll take this perspective of when we think about stacks, we mostly are just thinking about making systematic statements about the functor of points. Okay. So one thing that we want to do with these things is, I've alluded briefly to the analogy between working with these objects and the objects that arise in geometric invariant theory. So the first thing I'm about to do is sort of build out that analogy a bit more. So by analogy with GIT, we will spell this word correctly. We will stratify these moduli spaces by something which, for those of us who are used to doing p-adic analysis, things that look like Newton polygons, that's not the right name for them. We'll come to the right name in a moment, but things that sort of look like Newton polygons. And this will kind of identify various pieces of these moduli spaces as having various useful structures. So one of the pieces will be the piece that corresponds to the semi-stable objects, and that will somehow be a piece that corresponds to Galois representations or Étale local systems. And this will in turn help understand behavior of what I like to call period mappings. So we have a large class of interesting, not finite type, not sort of infinite Étale morphisms that show up in p-adic analytic geometry. And just to sort of give a few examples of names that can be associated with these things. So one of the earliest examples is the Gross-Hopkins period map that came out of studying formal groups. And then this was generalized by the work of Rappaport and Zink that Peter alluded to in his original lecture. And nowadays we have more, some examples. So there's a nice period mapping in the paper of Schulze-Weinstein on p-divisible groups, for instance. And then there's what we've been calling the Hodge-Tate period map, but to carry the formalism of naming it after people who actually worked with it rather than older names, maybe I should put like Cariani-Schulze here. But what I'm referring to is what we've been calling the Hodge-Tate period maps for coming out of infinite level Shimura varieties. So these kinds of objects, these kind of constructions, these are analogous to certain things we see in classical Hodge theory as well. They're period mappings out of things like certain moduli spaces of geometric objects, like K3 surfaces and cubic threefolds and so on. And what typically happens is you'll have some ambient space where this lives, and you'll have this period mapping, but it somehow doesn't always cover the whole space. It will be missing some stuff. And, well, if it does cover the whole space, then that tends to make it easier to study, for example, cohomology of local systems coming from the period mapping. But if there's some boundary, then things get a little bit complicated. But if you understand this geometry in terms of this kind of stratification, that will sort of let you fill things in the sense that, so a typical phenomenon, and this is really the sort of thing that Rich One and I were trying to get a handle on when we started thinking about this, and this was sort of our motivation, is that you'll see, well, so to speak, a Galois representation, but I really should say an État local system, on the image of a period mapping, which will be some sort of, this will be some sort of open subspace. Ooh, hello. Goodbye. Not quite. Right. So you'll see some sort of Galois representation, so to speak, on some piece of this space, which, if you think about only Galois representations or local systems, you can't sort of extend it any further. But if you pass to vector bundles, then the corresponding vector bundle will actually extend. So if you kind of transform from representations to vector bundles, then you actually get some sort of compactification of the structure. And this is somehow the point of what we were doing, is to try to exhibit these examples of compactifications. So this part of the picture is somehow the part of the work that hasn't actually been written yet, but this part of the difficulty was that the tools were rather crude at the time when we started doing this. Thankfully, the tools have gotten much better in the meantime, so this actually has a chance to get done. So that was somehow our motivation for getting into this. But that's not actually the target that I want to end up at here. So what I want to get to is, and sometimes I'm aiming for a definition, but it's a definition that leads to future developments. So this is essentially a program that I contribute. I'm going to write Peter here also, but maybe Peter says I should attribute this to Laurent Fargue. But anyway, I'll credit both of them here. So the idea here is to use these ideas to build objects analogous to those used in geometric Langlands, as considered by, for example, Drinfeld originally, and then Laurent Laforgue for GLN, and Vincent Laforgue for more general groups. Maybe I should put Genestier Laforgue. Perhaps is better attribution there. So these are called shtukas. My understanding is shtuka is a Russian word for thing. If you wanted to translate to English, I suggest, in the notes, I suggest some translations, things like gadget, whatchamacallit, pick your favorite. So there are certain objects, and I'll say a little bit about why that already in characteristic P geometry, characteristic p-algebraic geometry, it makes sense to consider them. The idea is we want to sort of introduce the analogous objects with the plan of realizing, in this case, it would be the local mixed characteristic Langlands correspondence, say for p-adic fields, in the cohomology of the moduli spaces of these things. And these are, again, very much going to be stacky objects. So I'll just write moduli stacks, actually, of these objects. So Laurent Fary has some very far-reaching conjectures that sort of map out a program here. I'm not going to try to expose that program at all, really, other than to get to the definition of the basic object. So this is in some sense an introduction to Farg's program without actually getting to Farg's program, because, well, one can only do so much in 4 lectures. And maybe one final comment, which I'll try to amplify very briefly at the end. This ties back nicely to existing concepts in p-adic Hodge theory. Such as the concept of a crystalline representation. But I'll try to say a little bit about that right at the end. Okay, so there's a lot to do. Let's get cracking. Okay, so let me go back to where we were at the end of last time. So for the moment, let me start out by talking about the case where everything is sitting over an algebraically closed field. So we've seen this case now a couple of times. We've seen it in the last 2 lectures of Jared and also my previous lecture. So let me start by actually amplifying something that Jared mentioned right at the end of his talk. So Jared mentioned the fact that there's some sort of rough analogy between the Farg-Fontaine curve in this case and P1 over a field, a curve of genus 0, if you like. So that analogy informs the shape of the classification of vector bundles, but it doesn't quite predict it exactly. So the theorem from last time on Galois representations follows from a classification theorem for vector bundles. And so this is the thing that I mentioned had a funny history, which I won't repeat right now, just remind you to say rewatch the end of the previous lecture. So the theorem says that every vector bundle on this curve over an algebraically closed field splits as a direct sum of, well, if this were exactly like P1, it would be a direct sum of the line bundles, namely the powers of O of 1. However, things are a little bit different here because the standard objects you have here are not just indexed by integers, but they're also indexed by rational numbers, and they're no longer line bundles. So these are the building blocks. So you might not be surprised by this, actually. If you think about the Dieudonné-Manin classification of isocrystals over an algebraically closed field, then again, you have a theorem that says that those objects split, but the basic objects are not just rank 1 objects, they're also these higher rank building blocks that are parametrized by rational numbers. So concretely, what are these things? Remember, I like to specify vector bundles on this curve by specifying phi equivariant bundles on the cover. So if D is a rational number, then O of D corresponds to a rank S phi equivariant vector bundle on the upstairs space, where the isomorphism with its Frobenius pullback has the form, well, if I take these basis vectors for the pullback, so there's a certain basis that has this shape, this will correspond to V2, this one will correspond to Vs, this one will correspond to P to the minus R times V1. So if you want, you can think of this, maybe I'll just mention, you can view this bundle O of D as a push forward of a rank 1 bundle, line bundle, on a degree S unramified tall cover, I should say a tall cover of XS, which is namely, instead of quotienting by phi to the Z, I quotient by not all of Frobenius, but some finite index subgroup. That gives me a different curve-looking object that has a lot of the similar properties, and this thing is really, so to speak, the O of R for that guy pushed forward down here. So you need these building blocks. Of course, I'm implicitly writing this in lowest terms. If this is not in lowest terms, then this construction will split into pieces corresponding to the right, the lowest terms representation of the fraction. And I should say O of D is semi-stable. It actually has the stronger property of being stable of slope D. So stable, semi-stable means, you know, none of the objects in the middle have a strictly larger slope. Semi-stable says you can't even, stable says you can't even have a tie. So an object will be semi-stable of degree 0 if and only if these building blocks all happen to look like O of 0. And that will end up giving you the construction of the Galois representations that we saw last time. Okay, so what about if F is not algebraically closed? Well, you certainly don't have any sort of classification result like this, but you do have some partial information that descends. So this decomposition is not sufficiently canonical to descend in any meaningful way. Even if you only consider, say, the isotypical decomposition, where you group together all of the terms of the same slope, that still doesn't descend, but in some sense, an associated filtration of that does descend and corresponds to the following. So in general, on a general field, I should say, perfectoid field of characteristic P, every vector bundle on this curve has a unique filtration. So I'll start with 0, which I'll call the 0 step, and then there's a 1 step, and then there's some step at the top, we're going to just run out of steps, where each of these successive quotients is semi-stable of some slope, call it mu I, and these slopes have to occur in descending order. So essentially, what happens is, so if you have an object which is semi-stable, then it will just be the unique step here. You will just go from 0 directly to that object, and then you will have one semi-stable quotient. So what this is saying is if you have something which is not semi-stable, then you can always find some kind of optimal, some object that sort of maximally falsifies the hypothesis that it's semi-stable. That's what this V1 is doing. This V1 is sometimes called a maximal destabilizing subbundle. You can read more in the notes about the sort of formalism of slopes. This is actually a surprisingly formal statement just by itself. So in the original context of vector bundles on algebraic curves, these filtrations were constructed by Harder Narasimhan. And so they're called, I will typically call them HN filtrations for Harder Narasimhan. Although I was told that I should be careful because people might think this means Hodge-Newton, which is a pair of names that you see often in crystalline cohomology. But here I mean Harder Narasimhan. So there's a filtration here that when you're semi-stable is a trivial filtration, but otherwise it sort of identifies some sort of optimal obstruction to being semi-stable. And when you have a filtration and you have some numerical invariance associated with the quotients, it's natural to make something like a Newton polygon. So you can make associate to V a sort of Newton polygon where you have slopes. Each mu I occurs as a slope with multiplicity the rank of the corresponding quotient. I should have said, in this filtration, these quotients are actually bundles. So, right, if you imagine a sequence and a general inclusion of two bundles on a curve, there might be some torsion in the quotient. In this case, these quotients are actually vector bundles. That's part of the condition. And their ranks are some numbers that add up to the total rank of the bundle. And so this gives me some sense in which to draw a Newton polygon. So, so in the notes, I'm drawing Newton polygons concave down. So I would start with the biggest slope. So the slope of this line would be some slope. So this would be, and the horizontal displacement would be some rank. So of course the vertical slope would be, the vertical part would be a degree. So the slope is slope. And so I start with V1 and then V2 over V1 and so on. And now there is not so much you could say about these slopes just from this lemma definition if you don't know anything else. So you can define filtrations and slopes in rather general contexts. I give quite a few examples in the notes. But when you do that, you don't know a lot of things. For example, you don't know what happens when you take the tensor product of two objects. What does that say about the slopes? This is a rather, this construction, again, like the definition of semi-stability, this construction is somewhat characterized by the absence of additional subbundles. So in some ways, it's also kind of a negative condition. So it's important to know that you have sort of a positive characterization of say, semi-stable objects, which we got from the theorem last time. So the addition, and so if you want the classification of vector bundles, sort of adds a lot of content to a construction that would otherwise be somewhat formal. So you can ask a lot of questions about how can these slopes interact. For example, one of the questions that was posed to the projects group, which I think they will have some report on next time, is if you have a short exact sequence, what can you say about the possible polygons associated to the three terms? And so that's an interesting question. I will, oops, I think I got my numbers wrong here. I will leave them to say what they can say about it. I want to say a couple of things about how these polygons, which again were some kind of replica of some concept arising from geometric invariant theory, how do these things interact with considering not bundles on an individual curve, but bundles over vector bundles on a curve over a base. So now, so let S be, say, any perfectoid space in characteristic P. And so let V be a vector bundle of some rank on, I don't care what the rank is right now, on this relative Fard-Fontaine curve. So now we can say a bunch of things about this. So one easy thing to say is that the degree is locally constant. So up to taking some decomposition into closed open pieces, you can imagine that the degree is going to stay constant. What does that mean about the polygons? So what I'm about to do is start considering the various fibers. So each point has a curve over it and a bundle on that. So I'm going to consider fibers of this bundle. And I want to consider the polygon, the Harder narrow-symptom polygon of those things, as a function of the base. So I will have a family of polygons, and I want to know how they vary. And this first statement is saying that, well, I've sort of normalized things so that the bottom left stays put. I'm kind of drawing everything coming out of the bottom left. So this degree is, right, the rank is somehow so of course the rank, I should say, the rank is also locally constant. That's not hard to see. And the degree is also locally constant. So the other endpoint, right, the coordinates of the other endpoint are the total rank and the total degree. So this is also staying locally constant. So what's going to happen as I vary the point in the base is that I have these sort of fixed endpoints, and I have some polygon that's bopping around between two fixed endpoints. And the question is, well, what can it do exactly? Well, it can't just do anything. It's very constrained. So I'm going to view the HN polygon of the fiber as a function on the base S. Is upper semi-continuous. It can jump up on specialization, but it can't jump down. So, for example, one consequence of this is that remember, semi-stable is equivalent to saying that this polygon is just a straight line segment. Right? Semi-stable means there's one slope, one step in the filtration and one slope, so one line segment of one slope. So semi-stable is somehow the lowest possible position. So if I've gotten my up and down right, this should say that the semi-stable locus is actually an open subspace of S. I can sort of break one way but not the other. And in general, I get a locally closed stratification. By polygons. And again, this is what happens in geometric invariant theory when you do the analogous thing with vector bundles on say, a family of curves over some base. Okay. So this is the sense in which there is a stratification by polygons on the moduli space of vector bundles. Well, without telling you what is the moduli space of vector bundles, well, I can at least consider the maps from any given thing into it. Any map from some test object into the moduli space corresponds to a vector bundle on the associated relative Farg-Fontaine curve. And I'm saying each of those things has a canonical stratification. And because those stratifications are canonical, they commute with arbitrary pullbacks. And so that really means that I have a stratification of this stack, whatever that is. And in particular, the semi-stable moduli of semi-stable bundles will form an open substack. Again, whatever that means. I essentially have given that statement meaning. This is sort of the usual thing that algebraic geometers do when stacks are hard. Can someone remind me what my target end time is? 10:58. Okay, I'm going to make a note of that. Okay. So I have the stratification of the moduli stack of vector bundles on Farg-Fontaine curves with an open substack of semi-stable objects and a locally closed stratification the rest of the way. Now this open substack has a special feature, which I alluded to earlier, which is the generalization of what happens when you have this over a point. Remember, over a point, if I have a semi-stable vector bundle of degree 0, then I get a Galois representation out of it. So if V is everywhere semi-stable of degree 0, meaning on each fiber, I should say maybe fiber-wise, semi-stable of degree 0, then V corresponds to a unique, well, whatever the analog of a Galois representation is. The correct analog is an étale QP local system, but maybe I should write QP underscore local system, because what I really mean is a sheaf, a pro-étale sheaf. So we've seen this concept of a pro-étale topology where you allow sort of not just étale morphisms, but the sort of infinite stacks of. So you can use here the definition that Pargov gave, where you just have sort of regular étale covers and then finite étale towers on top of those. That's adequate. So we have the locally constant sheaf QP, which we've seen in a couple of lectures already. Right. The sections on this would be continuous maps from underlying topological space to QP as a topological space. This is a sheaf of rings, so I can talk about QP modules on this, which are locally finite free. So these things, if you are in the situation where your base is connected, you can express this in terms of a certain étale fundamental group introduced by de Jong. It's not a profinite fundamental group because in analytic geometry, part of the point of doing analytic geometry rather than algebraic geometry is that there are lots of interesting examples of covering space maps that are not finite. This pen is, I don't know if this pen is any better.
When you say locally finite free, is it étal locally or pro-étal?
Pro-étal locally. It's a pro-étal sheaf, which is pro-étal locally finite free. So, right, if I think about a point, what am I saying? So a pro-étal sheaf of QP modules over a point, well, I'm going to specify it on not the SPA of the original field, but maybe SPA of a complete algebraic closure. So I give some QP vector space on that. And then, so it locally finite free means it's a finite dimensional QP vector space. And then to say that it's a sheaf means I have to, it has to satisfy the sheaf axiom for this covering, by the covering by an algebraic closure, and that's the Galois action. So this, in the case of a point, this is just a continuous representation of Galois on a finite dimensional QP vector space. But this is the geometric version of this, where you replace the Galois group, right? You still have the coefficients are still, so to speak, finite dimensional QP vector spaces, but the Galois group has been replaced by, well, in the connected case, it's being replaced by a fundamental group.
So maybe in the previous line, do you want to say pro-étal QP local system?
Yeah, I've been calling these things étal QP local systems. Well, I'm not the only one. But yeah, technically these are pro-étal QP local systems. But the terminology étal QP local system is actually quite entrenched. So you're just supposed to understand that it's pro. Okay. So this generalizes the correspondence with vector bundles, and so I say if you take one of these pictures I drew at the beginning of some sort of geometric period mapping onto some period space, then the idea is that you're going to get some vector bundle on that space where on the semi-stable of degree 0 locus you get some étal local system, which is the one that somehow corresponds to the geometric construction upstairs. So, so this is in some sense envisioned in, for example, the work of Rappaport-Zink. Okay, great. So sorry, I was in the process, I drew this to illustrate the fact that, the point of drawing this example, this is the Tate uniformization. This is to emphasize the fact that these things are not just ZP local systems with P inverted, because there are these covers like this that are, right, you have this is a discrete cover with deck transformations by Z. This is somehow not something that comes from the deck transformations aren't a compact group. And things like the Hodge-Tate period map and other things of that sort give you even more exotic examples of that. And maybe I'll just mention in passing without writing it down, some of this can be formally promoted to, instead of vector bundles, which are GLN torses, you take G torses for some more general group. But there are some technicalities I don't want to go into right now. So let me just stick to the GLN case for the moment. Okay. So I'm supposed to give some idea of what a shtuka is. So maybe I'm going to skip over. Wow, that's not so good. So let me very quickly mention. So when Drinfeld originally introduced this concept of a shtuka, the motivation is a fact called, nowadays called Drinfeld's lemma, which basically says the following. In characteristic 0, at least pro-finite fundamental groups of varieties over an algebraically closed field behave like topological things. So if K equals K bar, is a field of characteristic 0, then the profinite fundamental group of a product of two varieties over this, or somewhat more general schemes, but let me be sloppy just for time. Basically, the product of varieties has profinite fundamental group equal to the product of the fundamental groups. So you have some kind of, so these profinite fundamental groups are close enough to topological things. So for example, if X is proper, then finite Étale covers literally are the same thing as covering, finite covering space mapped to the underlying topological space by some argument using the Gaga principle. So somehow in characteristic 0, products, so under some hypotheses. So first of all, these things had better be connected, so fundamental groups actually make sense. But you also need something like quasi-compact, quasi-separators. Now this typically fails in characteristic P, because, for example, if you take the affine line over an algebraically closed field, well, the first thing you remember is that's very non-simply connected. There are lots and lots of finite Étale covers of A1 in characteristic P coming from things like Art and Schreier covers. Give you lots of examples. Right? There's a whole body of work by Reynaud, Harbader, and some of their mathematical descendants revolving around questions like this. And the product is somehow much worse. The fundamental group of the product is not the product of these fundamental groups, but there is a relation that somehow involves dividing by the action of Frobenius. So there's a relation of the form something like, so I'm going to write this in a very kind of crude way. For X, say perfect schemes over FP, perfect schemes right now. There is a perfectoid version of this in a moment. So these had better be, of course, connected, and I have to choose base points, and I have to do a lot of things. But so you don't get to take, clearly you shouldn't do this, because FP is not even algebraically closed. So this is completely ridiculous. But what you can do is you can divide by, so to speak, divide by Frobenius on one side or the other, it doesn't matter which one, and you get the right answer. So what does this mean? So these things are built out of finite Étale coverings of Y in much the same way that the Galois group of a field somehow has to do with the finite Étale algebras over that field and how they map to some particular algebraic closure. That choice of the algebraic closure is like a base point in topology. So when you do finite Étale covers, there's some notion of a fiber functor and blah, blah, blah. But in any case, the key point is that this is some sort of object that's built out of finite Étale covers of the scheme. When I put this formal quotient in here, which you could interpret in some very stacky way, but the concrete way to interpret it is as phi, so to speak, phi y, in this case, equivariant finite Étale covers. Right, it's the usual deal where, so the way you divide by an object is you consider equivariant things over it. That's the stacky way, or the classifying spaces in algebraic topology way. So there's a lot of discussion of this in the notes. In particular, there is an analog for perfectoid spaces, which was introduced by Peter in his Berkeley lecture course. So I talked more about this in the notes. This already has some very interesting applications in p-adic Hodge theory, which I won't talk about, but so-called multivariate phi gamma modules, just mention that. But to get to the point, I'm going to say something in like 30 seconds about what a shtuka should be in this context. So Drinfeld's shtukas so the idea is these are introduced to study the Langlands correspondence for the function field of some curve in characteristic P. So the idea is, these are some kind of things associated to some test object. So a Drinfeld shtuka over a base would be a vector bundle on the product. So this base is some perfect scheme in characteristic P, say. Plus what I'll characterize as not quite an isomorphism between this thing, say V, and its pullback along the Frobenius on S. So I take the Frobenius on S and the identity on C, and I use that as a map. I pull back by that, and I specify not quite an isomorphism. What I mean not quite an isomorphism means I allow poles along some sections of this projection, which are called the legs of the shtuka. Well, technically, that of a section is a graph of some map from S to C, and maybe you call that the leg. But anyway, so you have this surface, you have this Frobenius on one side, which is not quite an isomorphism. Okay. So similarly, in sort of analytic world, in the analytic world, so now we want to consider sort of replacing C with some local object. Well, it would be nice if I could take the diamond of QP, but I have to do something slightly technical, which, because of crickets, I won't have time to say much about. But let me just kind of throw the formal picture on the board. That will sort of finish the answer to the question that came up at the end of last lecture. So instead of this test curve times a base, so this will now become a perfectoid, or maybe a diamond, but let's simply just say this for a perfectoid in characteristic P. I want to replace this with the diamond associated to ZP. So I need to take some sort of absolute product of these things, and then some bundle with not quite an isomorphism on that. So what is this? Well, I claim this is actually the diamond associated to something reasonable and something familiar. First, let me tell you about this thing, which is slightly smaller. If I take spod QP, the absolute product of that with S, this turns out to be the diamond associated to the unwound version of the relative Farg-Fontaine curve. This is not a difficult calculation, but I won't say it here. You can look in the notes for more information. So this is somehow the point that reconciles what people were doing with these relative Farg-Fontaine curves and this formal analogy with local Langlands, that this construction, which we already had sitting around and already had a lot of use for, and we're already trying to study for other reasons, also turns out to be very closely related to something we're supposed to consider from the point of view of transporting geometric Langlands over to this mixed characteristic setup. So this thing is not quite that. So here, remember, I took out both sort of P equals 0 and something else. This guy, as you might expect, doesn't have P inverted, so I have to sort of put the P equals 0 part back in to get this. So SPA of A inf. Remember, so if S is a SPA RR plus, A inf is the Witt vectors of R plus. So I had that not quite analytic space, and if I cut out this much, this is enough to make it analytic, and then what I'm looking at here is really the diamond on this. So I'm really looking at some sort of vector bundles on this object. Sorry. This should be a diamond superscript. This should be a diamond superscript. These are right though. Yeah. So this is the diamond associated. These are the diamonds associated to certain actual adic spaces, at least when S is in this case. And then what I'm going to be talking about by the vector bundles are actual vector bundles on these things. And then the not quite an isomorphism will again be some kind of sections. But let me just end by saying that the sections, the legs, they're maps from, as I said, they correspond to maps here from S to C. Here, they correspond maps like this, as the whole point of what Jared set up last time is that these are untilts. So for example, so somehow these shtukas, if you have some legs, they are gadgets that involve data of particular untilts of something in characteristic P. And so the moral of this story is that in p-adic Hodge theory, we've always been traditionally starting from objects up in characteristic 0, like QP or something, and then making constructions that allow us to tilt. And that, of course, gives us a tilt, but with a privileged choice of an untilt. So essentially, in that world, it's very natural to look at shtukas with one leg. The one corresponding to the untilt. And those objects actually have been seen before. They are related to what are called Breuil-Kissen modules, which we'll see in Pargov's talk, I think. But what this formal analogy is telling us is we should be doing more. We should be looking at multiple untilts at the same time, which is something that probably p-adic Hodge theorists would not have thought to do otherwise. So this sort of point of view has opened up a direction that, there's more to say about this, but that will be the subject for somebody else's lecture course some other time. So, thank you.
Questions? Or maybe I should say one question, because we are late for the break.
Sujata has one question, looks like.
Is there some way that the strata can capture, special representations like Diram, crystalline, and so on? Yes.
So I will give a very cursory answer to that question. So special representations in the sense of Fontaine do correspond to certain additional structures. So for example, Diram representations correspond to, in the picture you have of a Farad-Fontaine curve, it will come with a distinguished untilt because you're implicitly starting from somewhere in characteristic 0. And the Diram condition will have something to do with the formal neighborhood of the Farad-Fontaine curve at that untilt. Yes?
Okay, wonderful. We'll resume at 11:30 sharp.